Welcome. I'm going to go ahead and solve these elevator problems step by step. All right, so here we go. We have a person in an elevator. I have to think about what forces are on them, right? Okay, so is there a gravity force? Yep, straight down. Is there a surface supporting? Yes, I'll call that a normal force. That's up. And there's no separate applied force. The entire elevator may be on a cable, but a person within an elevator in a normal elevator is not on a cable. So there's no tension force, and we're going to ignore friction. So this is the same free body diagram for all elevator problems is this, okay? Now, if we kind of use those little rules that we were talking about the other day, all right, I don't have them right in front of me. But the first step is free body diagram and label the forces. The next is to put in the data. Okay. Now, the key to elevator problems is realizing that the scale is the normal force. Scales don't tell you how hard you push down on them. They tell you how hard they have to work to keep you supported. In a bathroom, these will be balanced. In an elevator, not always, okay? So when they tell you the scale reads 700, you must realize that's the normal force. That is the first thing. And the second is, in order to get the weight, you're going to need the mass. So the first two steps are, free body diagram, which we've done, listing data. I'm going to list the mass over here. Okay. The third step is mass is not weight. So if they gave you the weight of the person, you would just put that in, but they didn't. They gave the mass. So we're going to use the mass to figure out the weight according to the formula F sub G equals mg. So let's just plug in. F sub G equals 51 kilograms times negative 9.81 meters per second squared. Okay. If I do the math there, I get F sub G is a negative 500 newtons. Okay. So guess what? I picked an easy number, so this would work out really nicely. Now, the next step will be components. We don't have any. And the next step is to write specific forms of F net equals ma. This is the whole point of drawing a free body diagrams. Now, we only have one direction that's of interest. That's the vertical direction. And I have two forces, a normal and a gravity that I will expect to be negative. Okay. This formula is also the same for every elevator problem. Okay. All right. Now, when we're all done here, I can now plug and chug. So I'm just going to plug and chug into this formula here. So I guess I'll do it over here. So let me see. We got 700 newtons plus a negative 500 newtons equals the mass, which is 51 kilograms, times A. If I do the math there, I get the acceleration is 3.9 meters per second squared, and that works out to be a positive number. Okay, that makes sense because this is bigger than this. All right, now if he's going up, is he at the beginning, middle, or end of his ride? Well, the acceleration is up and the velocity is up. Okay, when this is true, this is called speeding up. And guess what part of the ride you speed up on? The beginning. Okay, so he's at the beginning. If, on the other hand, if he was going down, could he possibly have this acceleration? And if so, what part? Well, this would still be an upward acceleration, but now he'd be going down. This is slowing down. And you slow down at the end of the ride. Remember, a typical elevator ride, you speed up at the beginning, you go at constant speed in the middle, and then you slow down in the end. All right. Everything's the same about all of these. So I'm just, again, have this exact same free body diagram, except now that the scale reads 300 newtons, okay, and the mass is still 51 kilograms. Since the mass is still 51 kilograms, we can still assume from the first problem that the weight is going to be negative 500 newtons. Okay, so we've done step 1 and step 2. Step 3 is to write specific forms of F net equals ma. And once again, I've got a normal and a gravity, and those both add up to ma. Okay, if I substitute in, I get 300 newtons minus 500 newtons equals 51 kilograms times acceleration, and the acceleration works out to be negative 3.9 meters per second squared. Okay, now the person is going up. The acceleration is down because it's negative. This person is slowing down, and so we must be at the end of the ride. Okay. Now we've got this same elevator, but now the Fn is now 500 500. The Fg is still negative 500 because they got the same mass. That hasn't changed. And the formula again is going to be Fn plus Fg, equals ma. So 500 minus 500 equals 51 kilograms times A. You will get that A equals 0. If he's going at constant velocity, he's at the middle of the ride. And finally, the last one. We have a force of gravity still. The mass hasn't changed, so that's still negative 500 newtons. But now there is no force normal. Okay? So when you do your F net equals ma, and you look at your picture, there is no more normal force. There's only a gravity force. That equals ma. All right? So if I plug in negative 500 newtons equals 51 kilograms times A, I will get that A is negative 9.8 meters per second squared. Guess what this person's doing? They are falling, and we could also say they were weightless because they're falling at the same rate as their container, just like someone on in orbit does, or on the Vomit Comet. Hope that helped.